Okay, welcome to grade 11 college math. We are starting a new unit, unit 7, and this is in chapter 4 of your textbook. Our first lesson is a two-part lesson. The first one is, again, familiarizing ourselves with modeling of quadratic relations. So what they look like, how we draw them, and some characteristics of them. And then we talk about the shape it forms as a parabola, and so we talk about some of the characteristics of the parabola. So let's first of all introduce how we come up with quadratic relations versus something like linear, which we've done in the past. So when we let's say we plot these two, and then we'll see if they become obvious. So we plot the points and draw a graph for each of these. So we're going to plot these points. So at x4, -3, we have a point, and at 5, 0, at 6, 3, and at 7, 6, and at 8, 9. So what are we seeing here? Well, we're seeing, and forgive me for not having a ruler with this set of tools, but we should have a straight line. If I do it by hand, it's not as great, but and we would call this linear. All right, on this side, we have -1, -3. We have 0, -4. We have 1, -3. We have 2, 0. And we have 3, 5. Okay, so we see this curve happening. And we, from previous knowledge, kind of know that this is going to be symmetrical. So in this case, we call this a, I'll say it is quadratic. Oh, we need our eraser. There we go. We need, this is going to be quadratic. Okay, so linear versus quadratic. The graph of linear equation is when we have an equation like this. Y equals slope times x plus the y-intercept. This always forms a straight line. That's a giveaway. That's definitely what happens in a linear equation. The graph for a quadratic equation is in this form. Y equals a number in front of x squared plus a number in front of x plus c. And those numbers could be 1, it could be 0, but usually it's 1 or another number. And these are called parabolic curves. Okay, so one way to tell is obviously by a table of values and by its image, a straight line versus a U-shaped curve. Another way is to look at the first and second differences. So this should ring a bell from first differences in grade 9, second differences in grade 10. When we look at first differences, we see that for every spaced x value, we find the differences between the consecutive y values. In the second differences, we determine the differences between the consecutive first difference values. So let's show this. So you would say, this, the bottom number, subtract the second number. So 4 minus 7. I like to always do from the bottom, subtract the top. From the next lower one, subtract the one above. and I find that is always more consistent. So that gives us negative 3. Now what about this one? So 1 minus 4 is negative 3. Negative 2 minus 1 is also negative 3. So we see a pattern develop. So here's an interesting one. So remember your interval or integers. We're going to say negative 5 minus 2. Well, that makes a plus sign. Minus and minus. So we're actually saying negative 5 plus 2 is negative 3. Let's try that again. So negative 8 minus 5. That makes it positive. So negative 3 plus 5 is negative 3. So this is consistent. This is a constant. Therefore linear. If this constant is in the first differences, it's linear. Let's obviously do an example where we're going to see, let's just say, make a point here. All first differences are the same, so the equation is linear. All right, let's try this next one. So again, negative 1 minus 0 is negative 1. 0 minus 1 is plus 1, because that becomes a plus. Okay, and then, so let's do that. Here we go. 3 minus 0 is 3. 8 minus 3 is 5. And 15 minus 8 is 7. So this is not constant. Not linear. So when that's the case, we don't know what it is, so we have to go to the next level. So the second difference is, so 1 minus 1, that's going to be a plus sign, so 1 plus 1 is 2. All right. 3 minus 1 is 2. 5 minus 3 is also 2. 7 minus 5 is also 2. So now we see constant. Therefore, quadratic. Okay, so let's summarize this. First differences are different, but all second differences are the same, so the equation is quadratic. Very good. All right. I hope that rings a bell. I hope that's brings back some memories. All right, so that's two ways we can do it. Look at it graphically. We can look at it with the table of values to tell the difference between linear and quadratic. Well, let's get some definitions here. So a parabola is a symmetrical U-shape curve that opens up or down that's kind of up or space down. And the graph of a quadratic quadratic relation. Okay, let's hope our next definition isn't as long. This vertex, what is the vertex? It's the lowest. So a min or highest, a max, point on a parabola that opens up or down. So again, our notes are going a little over. So what is in something that opens up? We have the lowest point is the minimum on a parabola that opens up. So again, if you had a parabola like this is the min. Okay, the max is the highest point on a parabola that opens down. So look at this parabola, right? Opens downwards. We have a max point. Okay, so how can we tell if something is linear or quadratic? How to tell? If the graph is a parabola, it is quadratic, obviously. If the first differences are constant, then it's linear. If the second differences are constant, then it's quadratic. Okay, if the degree of the polynomial is 1, so it has an x term of only, an x to the 1, it is a linear. An example, y equals mx plus b, the x is x to the power of 1. In a quadratic, there's a quadratic, we have, let's say y equals ax squared plus bx plus c. We're interested in this one, x squared. Okay. So those are clear indications that we're looking at a quadratic when we see those clues. So for each example, evaluate or estimate for x equals 2 and identify whether it is quadratic or linear. So what we do is substitute x2 in for this. So y equals -3 x2, so the 2 goes in for x squared, and so we say -3. Now BEDMAS, order of operation, tells us to do inside this and then square it. So we have 3 squared plus 1. We have to do this in the right order. We also use our calculator. Our calculator will do this properly. So we have -3 times 9 plus 1. So we're going to have in the end here y equals, let's just punch that in. So -3 times 9 is 27 plus 1 gives us -26. All right. Well, it gives us a minimum, or no, it gives us a, it gives us a maximum of -26. But anyways, what is this? So this one, A is going to be quadratic. How do we know? Because of the squared symbol. Okay. Now the next one. Well, we can identify it fairly easily. So we're going to substitute 2 times 2 minus y plus 7 equals 0. One thing I like to do when I have a negative y is I bring it over, and that changes the sign to a positive. So then I have, back on this side, I have 2 times 2 is 4, and I have the 7 is here. So now I have 11 equals y. So again, it's kind of irrelevant that we're figuring out for y. What we really want to focus is what is the exponent on the x, and it's just a 1. So we're talking about linear. Now, obviously, look at C. C is a straight line, so that's linear. D is a U-shaped curve, that's quadratic. It's as simple as that when we have it, when it's so obvious. Okay, how can we deal with an application problem? So, a football was thrown in the air. Its path can be modeled by the relationship here. And so these numbers, represent something. One tells us, whether it opens up or down, how steep it is. One tells us sort of where the midpoint is, and one tells us, this actually tells us where it left the ground, or how high was it when it first started. So h is the height of the football in meters, and t is time. Complete the table of values for this relationship. So what you actually have to do in each of these cases is you have to substitute t in for these. So if you substitute 0 in for t, we have t squared plus 20t and 150. Well, what's that going to do? That's going to be 0, and that's going to be 0, and we're going to get 1.5. So 1.5, the football was 1.5 meters off the ground. So think of the average height of a person who's throwing the football. This person's throwing a football, and they're 1.5 meters off the ground. All right, so I'll save us some time, but basically what we have to do here is we have to keep putting this number in. Okay, and if I do all that in my calculator, I do all this on my calculator, I get 16.5, and that number goes here. So hopefully you remember doing this. And again, we keep going through all of these. And so it's a bit time consuming, but you're going to rely on your calculator. It's not going to be too bad. And you're going to get 21.5. If I continue, I get 16.5 again with 3s. With 4s in there, I'm going to get 1.5. And with 5s, interesting enough, in 5, I'm going to get -23.5. Now, this doesn't really make a whole lot of sense because at 5, we're going to be down underground here. So really the ball doesn't go under the ground, the ball hits the ground and would bounce. But so let's plot this. Use your graph to estimate how long the ball was in the air. So let's try this out. So let's plot the graph. At 0, we're at 1.5. At 1 second, we're at 16.5. If that's 17, here's 16.5. Okay, at 2, we're at 20. Again, there's 22, there's 21, so right in between is 21.5. We start coming back down to 16.5 again at 3 seconds. At 4 seconds, we're at 1.5. And 5 seconds, we're way down here, and it's irrelevant because we're not going to talk about a negative height. So we can add our curve in here, try to make it symmetrical. You probably remember doing a lot of this last year. All right. From your graph, estimate how long the ball was in the air. So it started at 0 seconds and it traveled just past 4 seconds. So you might want to say 4 and a little bit, right? Sorry. Use your graph to estimate how long the ball was in the air. Okay, well, it went 1 second, 2 seconds, 3 seconds, 4 and a little bit. So maybe you want to say something like approximately 4.2 seconds. All right, use your graph to estimate the coordinates of the vertex. The vertex is the peak. So what would you say? Well, our vertex happened at 2 seconds, so that's our x term along the side, along the bottom, and then where our highest number was is here. So here's our vertex, right here, 21.5. Okay, explain the meaning. So our vertex was 2 and 21.5. This means at 2 seconds, the ball peaked at 21.5. What are they talking about? Meters, right? Good. Okay, or the max height. Explain the meaning of the data in the first row of the table. So this first row, what's happening here? Well, we call this the y-intercept, or initial value. In this case, the ball was thrown from a height of 1.5 meters. And we said at the beginning, like, that could be like the height of the person's arm, height of quarterback's arm, or shoulder, right? So we can kind of interpret those things by what we're reading. Okay, that's the introduction of how we model. We modeled it 3 different ways. We modeled it with we modeled it through graphs, we modeled it through tables, and we modeled it through equations, right? So we had equations, we had graphs, we had tables. So that tends to be the 3 ways we model quadratic and linear relations. All right, we're not done. We're going to go and just learn more again about, or remind ourselves more about, what the parabola is. So let's jump right over to this note here. So just part B of this note. And let's just, most of this is going to be a review for you guys. So the graph of a quadratic relation is called a parabola. The parabola has some important features. Okay, so what could we start with? Let's start with the vertex, right? And the vertex can tell us the max and the min, for example. All right, and this is a coordinate, x and y. All right. Now, what else might we be interested in? Well, here's our xy axis, right? So we have x, we have y, and we have 0 here. So when we cross the y-axis, we call that the y-intercept. Like we saw in the football example, the y-intercept was where the ball left, the height of the ball left. Okay? Now, where else? So let's say we're going up this parabola and we hit this place right here. And we hit one over here and one over here. Well, this whole line is called, the zero line. So meaning y equals 0. So where do the zeros happen? Well, right here and right here. So this is the 0, and some people call them the roots, like roots of a tree in the ground. So the tree's rooting itself in the zeros, or roots. Also called, aka, the x-intercept. So we have y-intercepts crossing the y. We have x-intercepts, usually 2 of them, sometimes 2 of them, called the zeros or the roots. So way too many names to remember, but it's all the same. All right, we have this imaginary dotted line. Okay, it's not a real line, but it's an imaginary dotted line going through the vertex. And we call that, if you remember, the axis. So axis is a line that things are symmetrical. So of symmetry. So symmetry means symmetrical, meaning equal on both sides. So along this axis, the left side is symmetrical to the right side. That's why we call it the axis of symmetry. We sometimes just do an abbreviation, AOS, to make a short form. We got one more thing down here. We have another imaginary dotted line going along this bottom, hitting the vertex. And we would have the optimal value. And we called this either a max or a min. Now, in this case, it's a min, right? Because we're going upwards, and we bottom out at the minimum, and we come up. Okay, so some important points there. We'll just, we'll draw a little max in here. Right, we'll get a max. Here we'll get a min. Okay, so keep going. This should ring a bell. Everything you ever wanted to know about parabolas. Well, parabolas can open up or down, like we saw over here. The 0 of a parabola is where the graph crosses the x-axis, like we saw right here. The x-axis is this line. It crosses it once or twice, and sometimes it doesn't touch it at all. But okay, the zeros can also be called x-intercepts or roots. So something we mentioned above. The axis of symmetry divides the parabola into 2 equal halves, symmetrical halves. Okay, the vertex of a parabola is the point where the axis of symmetry and the point I've lost my point here, and the parabola meet. Sorry, axis of symmetry and the parabola meet. It is the point where the parabola is at its maximum or minimum value. The optimal value is the value of the y coordinate of the vertex. The y-intercept of the parabola is where the graph crosses the y-axis. Again, very much a review from last year. Hopefully you remember some of this. Make everything come a little easier if you know the terminology. All right, so from these three examples, these three parabolas, can we just pick out the most important facts? And we have the characteristics along here, like vertex, optimal value, axis of symmetry, zeros, the direction of the opening, and the y-intercept. This is common that we identify these characteristics of the parabolas we see. So we have a point here, a vertex. Well, it's at 1, 2, 3. So it's at 3 and up 1. So 3, 1. What's its optimal value? Well, its optimal value is it comes down and it bottoms out right here at 1. So it has a min of 1. Axis of symmetry, again, it's this imaginary line going through here at x equals 3. What are the zeros? Well, interesting enough, look, it comes down, but it never touches this line. So we have no zeros, which is possible. And the direction of the opening is up, so we know we're going to have a min. Okay, and what's our y-intercept? Well, our y-intercept, if you notice, you follow this line, it comes up, it hits around here. Let's just, for simplistic, make things a little bit simpler. Well, we'll just make it even more simpler. We'll say it hits here. So we'll say 0. I know it's probably 6. It's probably 6.6 or something like this, but let's not make that so hard on ourselves. Let's just say it's 7. Sometimes the picture moves around a bit. Okay, the next one. Where's our vertex? Right here. So we're at -1 on the x and -4 on the y. We have an optimal value, so we have a minimum again of -4. Okay, so on the y it's a -4. What's our axis of symmetry? So coming through the center here, we are at x equals -1. Now we have some zeros. We have 2 zeros. We have a 0 at x equals, actually I like it when you write them as coordinates. So this is an x coordinate of -3 and a y coordinate, of course, of 0. At this line it's 0. And you have a +1 and 0. So 2 points. What's your direction of opening? Well, it opens up, meaning we have a minimum. And where's our y-intercept? Crosses right here. So our y-intercept is at 0, -3. All right, you try this one. So pause the video and you figure this one out. And then unpause the video and then I'll reveal our answers. All right, so I'm back and hopefully you did try it on your own. Here we have -3 and +5. So -3, +5. Our optimal value is up here. It's a max. A max of 5. We have an axis symmetry of coming through here at -3. we have zeros. Let's just say that's coming through right there and right there. Let's not use decimal values if we don't have to. So we have a -3 and 0, and we have a -1 and 0. Now, where's our direction of opening? Well, it's down, and we know we're going to have a max because of that. And then we have a y-intercept of 0 because it's on the 0 line, and we'll say it's passing through -3 right here, just to make things simpler. All right, there you go. So those are fun to practice. They're pretty straightforward to do. And here are some other facts. So try to solve these. So pause the video, try to quickly read through these and see if you can give a true or a false. And then unpause the video and I'll tell you which are the truths and the false. All right, let's take these up. So the axis of symmetry goes through the y-intercepts. No, not usually, because it's parallel to it. The vertex is always located halfway between the zeros. That is true. Okay, because it's symmetrical, so it's going to be equal amount away from both zeros. The y-coordinate of the vertex is always the same as the optimal value. That is true. The parabola must always have at least one x-intercept. False. Right? We had one of these. Look at this. Right? That never touched. So it's not. It's not always the case. Sometimes you have one. Like if you had a vertex that just touched the line, that's just one y or x-intercept. But anyway, we didn't have an example like that. But the x-coordinate of the vertex is always the same as the axis of symmetry. True. Yeah. So the vertex tells us the x-coordinate of it tells us the axis of symmetry, and it tells us the optimal value. The parabola must open up. Well, no, it can open up or down. The y-intercept is always positive. No, it can also be negative. So that's false. All right, so that summarizes, modeling of parabolas, what they look like, what they shape, how they look like in graphs, how they look like in table values, how they look like in equations, and we've also identified all the characteristics of a parabola. So thanks for listening to this longer than usual lesson, and we'll see you with the next